Yeah, thanks for having me. It's a great pleasure to be here and be given the opportunity to report on basically two projects I've been involved in. Maybe a little bit about my background. I have a PhD in plant breeding. And during my PhD, I was introduced to mixed models in the context of stability analysis, yield stability. And the work after the PhD also continued to be focused on plant breeding applications, plant variety tests, multi-environment trials, plant breeding trials, QTL mapping, and so forth. But also consulting was always part of the job. And so there were lots of other interesting applications and areas where statistical methodology could be employed with benefit. And this is two examples that actually also evolved in that way. So this is two projects, two PhD projects that I'm involved in. Both of them are related to the determination of economic optimum N rates. So here's a sketch where we have gross return, we have net return in green, and we have the N fertilizer cost in red. We cheated a bit. The intercept for the gross return and net returns is starting at zero intercept. So of course that's non-zero, but this makes it fit better into one figure. So the idea is that you have to balance the added output you get from any additional unit of N you put on against the cost, which is a linear function. And if you balance the two, you obtain the green curve, and where it has a zero slope, that's where the optimum N rate is, which is below the optimum, well, the possible maximum yield you can achieve. So experiments are conducted to determine economic optimum rates. And there's, of course, questions of model choice. There's questions of how many replicates do we need? How many levels do we need? And also questions around what is the optimal design to fit those models, or to be able to estimate those models. So one particular type of challenge is that we have different models, different types of models. So a common approach is to say, okay, we're going to fit a bunch of models, and then we're going to select the best fitting one based on some criterion, AIC, coefficient of determination, whatever. Seems suitable. And then we take the selected model and all the downstream inference, including estimation of economic optimum rates, significance tests, and so forth, are based on the selected model. But there's a post-selection problem, because the model selection itself is not taken into account when it comes to the inference. We pretend that that's the true model and the only model, but it's actually the case that we've done a bit of snooping and checking which model might be a good fit. And so taking that into account is actually a good idea. And one possible solution is known as model averaging. So this is going to be about model averaging. So when there's a single model, we can ask the question, what's the optimal design here? And optimal means, okay, how many N levels do we need? Where do we place the levels? How many replications do we need? But how does that play out when there's multiple models that we're going to average in the model averaging approach? So that's the topic of the first part of my talk here. So this is based on two papers, one of which is published, and the other one is still under review. And my collaborators here are Custodio Matavel and Andreas Meyer-Aurich from the Leibniz Institute of Agricultural Engineering and Bioeconomy in Potsdam, Germany. So they are agricultural economists. So I'm going to go briefly through a couple of models that are commonly used that you're probably all familiar with. One is the Mitscherlich function, a nonlinear response function, dose response function, which has an asymptote. And that's often a plausible model, because if the N rate is low, the extra you get from applying an extra unit of nitrogen, the increase is higher than when you're already at a very high level. So the idea that we're going to use here is that we can, of course, estimate the economic optimum rate, basically using the framework that I've shown on the graph earlier. So what's the point where the slope of the cost curve equals the slope of the production function in economic terms? And the solution for the Mitscherlich function is this one here. It's a nonlinear regression problem, so we're going to apply nonlinear least squares typically to fit that model. So how do we get the estimate of the economic optimum rate? Well, we could just use this equation here, but a more convenient approach is to actually do a parameter substitution. So we can actually take this equation for the economic optimum rate and rearrange it and have an equation for any one of the parameters of the model, such as the beta 1 in this case, and then plug that into the original equation. And then we have eliminated the beta 1 and replaced it with the economic optimum rate as a parameter of the model. And then we get the estimate of that parameter directly, the parameter of interest, including standard error and confidence interval and whatever we want to do in terms of inference. And we can do the same with the other models, like the quadratic model, where you've got an intercept plus a linear term plus a quadratic term, and the economic optimum rate is shown here. And in all of these equations, of course, you've got the price per unit of nitrogen, and you've got the price per unit of crop that's involved. And so to be able to determine that, you need to have the prices. And then we can make the same kind of substitution and have the reparameterized form, which is shown at the bottom here. Now, the quadratic model is a linear model in terms of how it's related to the parameters. But once we make this kind of replacement, it turns into a multiplicative model because we've got that product beta 2 times the economic optimum rate sitting in there. So that makes it an intrinsically nonlinear model because of that reparameterization, which is convenient if we want to get an estimate of the economic optimum rate. So here also, we're going to use nonlinear least squares. And then the quadratic can be modified into the quadratic plateau function, where you have a quadratic arm, and then where it reaches its maximum, it then levels out into a plateau. And then we can do the same kind of thing and have this definition here. You've got a two-part definition there, where the first part is where nitrogen is below the breakpoint, the amount of nitrogen that you put on. So N star is the breakpoint. And then beyond the breakpoint, it's a horizontal line. And finally, another common model is the linear plateau function, where you've got a linear increase up to a breakpoint, and then you've got a horizontal line. That seems to be a very popular model, and I've used it in other contexts as well, but it's kind of not so plausible because you would rather assume a smooth transition. The quadratic plateau does that because you can enforce the slope to be 0 exactly where the breakpoint is. But here you have this break and this change in slope, which is kind of convenient because you can say, okay, where the breakpoint is, that's where the economic optimum rate usually sits. But then it may not be so plausible. It may actually cause some bias if it's not a good approximation of the real underlying production. So model averaging. So rather than saying, okay, these are our candidates, and maybe there's a bunch of others, we're going to fit all of them and then do some kind of model selection exercise based on AIC or some other measure of fit. Why not just take the average? And that's a very, very popular method and very powerful method. And there's, if you do model averaging, then the key step is to determine the weights. So you can do an unweighted average. That's simple, but it's usually better to have a weighted average where you take a measure of goodness of fit, for example, such as AIC, to determine the weights. And a model that has a better measure of a better value for the measure of fit gets a higher weight in the averaging process. So here's this, the weight as defined based on AIC. This is a very nice paper by Steve Buckland in 1997, and I think it's biometrics. You can also estimate the average, so you can also fit each individual model, determine the economic optimum rate based on each individual model, and then take the average across those estimates and call that your best estimate of the economic optimum rate. That's a further option here. So here's an example. This is a field experiment at a site in Bavaria. The design was a randomized complete block design. The number of replications was 8, I believe, so a relatively large number of replications, a pretty big trial. And the N rates are shown here. So that's quite a large number of N rates. I think it's 11 different N rates. That's a lot of N rates. I guess they figured we want to be very fine-grained so we can really track the profile of the curve. But from a design perspective, using a very large number of points is not usually a good idea. It's usually good to have some, it's a trade-off between, I put a lot of, well, how do I put that? If I've only got it really depends on how many parameters my model has. Basically, the minimum number of points you need is given by the number of parameters that your model has. So my rule of thumb that I usually use is, okay, what's the number of parameters that my model has? And then plus 1 or 2. That gives me space to also test the lack of fit of the model, which is a good idea. A lack of fit that says, okay, I can saturate the model and have each level of N have its own mean independent of the other means. Whereas if you do a regression, all the means are connected through that nonlinear model. So anyway, that was the design. Randomized complete blocks, 5-factor field. And here are the estimates. So economic optimum rate for the 4 models that I've shown with confidence intervals, and the parameter estimates. So yeah, the confidence intervals are pretty wide. I mean, there's different ways to get to the confidence intervals. If you use nonlinear least squares, you will have a standard error, and then you can do plus minus your critical t-value times the standard error gives you a symmetric confidence interval. But there's other methods to get confidence intervals, and then some of them are asymmetrical. Anyway, this is fitting each of the models separately, and each returns a different estimate of the economic optimum rate. Now, in tackling the design problem being how many N levels and where do I place the N levels for a given capacity in terms of how many plots do I have? That's how we're going to frame the design problem. We're using a Bayesian framework. Just a few, not too much detail here, just to say it's a Bayesian analysis. We use the no U-turn sampler and compute, for example, 95% highest density intervals, the equivalent of your confidence interval in a Bayesian setting. And we have the weights in there. So how do we deal with the weights? We consider the weights to be hyperparameters in the Bayesian model. And then we can use a Dirichlet prior for the weights, and that distribution is quite suitable because it allows putting the constraint that the sum of the weights is 1, which is what you want for a weighted, for model averaging on the weights, the sum of the weights to be 1 exactly. So here's the same kind of, or similar kind of analysis using the Bayesian framework. And first, again, each of the models individually. So what you see here is really the individual fits, where each model has its own economic optimum rate estimate, plus the confidence intervals. And here's also the model weights based on that Bayesian framework when you put them jointly into a single model. I'll come to that single model. So that single model is really using this equation up here and basically regards that as one model. But it is really the average, the weighted average of the component. But it's then fitted as like a single model, essentially. So here are the individual fits, just visualized again, where you have the confidence interval, the Bayesian confidence intervals around the point estimates of economic optimum rate. And you see visually as well that they are in slightly different places. Got the linear plateau and so forth, the Mitscherlich, the quadratic plateau. Now, if you fit them as a combined model, in the end, you have a single function. And for that data set, this is what it looks like. So you've got and this is net return. And so you've got the optimum, the economic optimum here, and the economic optimum rate down here, 229 kilograms of nitrogen. And if you look at the components, so just to remind you, so you've got those components sitting in there, and each of those components is parameterized in terms of economic optimum rate. There's a single parameter for economic optimum rate now. So each of the component models now also has its optimum at the same point. So that's depicted here. That's really the special feature of this type of approach. So that's the analytical framework that we're using. And now let's turn to the design problem. So it's because it's a Bayesian framework, we need the usual components, we need the prior distribution of our parameters, we need the posterior distribution of the parameter vector given the data and the design phi, and the usual definitions are shown here. And if you want to optimize the design in a Bayesian framework, what you can do is define, you need to have an objective criterion, and that's a function of the different probability distributions that were shown on the previous slide, which basically act as weights of a function which measures the utility function. What is the utility of a specific design choice, denoted as psi by the group letter psi, for given data y and for given parameter vector beta. That's the small u here. That's the utility. And there's different choices you can make. The choice here is the Kullback-Leibler divergence, which is a measure of information gain as you proceed from prior to posterior. So in a nutshell, Bayesian statistics means you've got a prior distribution that encapsulates all the prior information you have on the parameters. Then you conduct an experiment that provides data, and then you combine the data with your prior information and produce what is called the posterior. So the posterior is like an update to your prior after having incorporated the data. That's in a nutshell is the key idea. And the utility here is how much change in shift in parameters or in your parameter distribution, the whole distribution, do you get when you ingest the data into the prior. And that is a function of the design. So that's the objective function up there, which uses that utility function. And so the question is, what is the design psi that maximizes this utility? There's an integration involved. It's integrating across the parameters, and it's across the distribution of the parameters, and it's integrating across the data. At the design stage, we don't have data, but our prior distribution has the distribution model included for the data, and also there's the prior for the parameters. We have an assumed distribution for the data, the likelihood. That's all included there, and we just integrate them out. So we have a function that in the end only depends on the design. That's the nice thing about it. And then we can optimize that. That's done numerically using numerical search methods. There's different ways this can be done. We used one particular method that's called stochastic optimization that's shown here. So it's a gradual change. You have some start configuration, say that's my start design, and then can I improve this by taking small steps away from where I currently am? And you keep moving along the gradient. You take into account the gradient. That tells you which direction you should be taking the next step. And there's some stochasticity built into the search algorithm. And in the end, hopefully, we get somewhere near the optimum. So we've now applied this to the same experiment, same dimensions, basically. We assume that we have 120 plots. So the optimal design, of course, we can also ask, okay, how many plots do we need? You can actually solve that problem like in 2 steps. You can say, okay, given a certain number of plots, what's the optimal design? But then you can also ask, okay, how many plots do I need? And the 2 together will then give you the final design. But oftentimes you have like a capacity. This is the total number of plots that we've got available. But otherwise, you can say I'm leaving out that second step that tells me how many plots overall do I need. So given we've got 120 plots, and assuming that this combined model, this average model, is the model that we're contemplating, what is the optimal design? So a second specification that needs to be made to get this thing to run is we need to actually specify how many points do we want. So that algorithm can handle a search where we say we want 4 points. Given that we want 4 points, where should we put them? So it's conditional. So we will actually need 2 steps to find the optimum. We'll just do a grid search and look at a couple of numbers of points. 4, 5, 6, 8, and 10 is what we chose. And then we can determine which of those works best. Why did we choose those? Well, for illustration, it's nice because we can have equally replicated designs, meaning that each level of n has the same number of reps, because each of those divides 120. So if you have 120 plots and you have 4 levels, then you can do 30 reps. So that's a pretty large number of replications, of course. Anyway. So here's the result of that optimization. So the first is where you say we want 4 levels, and these are the levels that come out. And so forth. For 5, here's the optimum, and the number of levels is 5. Yeah. And finally, for 10. So these are all odd numbers, really, and it's also not, there's not such a clear pattern, except that there's a tendency for the spread of values to extend a little bit, but even that is not so clear cut, which is interesting. But it's quite typical, actually, when it comes to design for intrinsically nonlinear models, and this is clearly intrinsically nonlinear. So but these designs are all conditional on the number of n levels that we want to use. But which of those should we use in the end? To tackle that question, we did a simulation where, again, we used the same model, and we used the whole set of assumptions inbuilt into the Bayesian framework to simulate data, assuming an economic optimum n rate of 150, 55, which is close to what we actually found for the experiment. And we did we did 10,000 simulation runs. And in the simulations, we assessed the bias, the variance, and the mean squared error for the economic optimum rate estimate. And here's the result. So this should be mean squared error. So the mean squared error is lowest when oh, this is the economic optimum. This is bias. So here's the bias. The bias tends to go down. It's going up here again, which is somewhat surprising. But the optimum in terms of bias is when you do 6 levels. And here's a plot that shows both the mean squared error and the variance as well. So the mean squared error is the sum of the variance and the bias squared. So bias, systematic error, systematically over or underestimating, and variance is just how volatile are you around the expected value of what your estimator produces. So here we can also clearly see that the best design has six N rates. And yeah, that's interesting that you can get away with 6 here, and you don't need 10. And certainly, you know, 4 and 5. 4 is the smallest that we used, but 6 is clearly the winner here. Yeah, so that's that. So this provides a framework that allows us to make a choice based on a set of models that we're contemplating, putting them into this averaging framework, and then working out, first of all, for a given number of N values, where do we place the N rates? And we need to figure that out because we need the conditional optimum given the number of N levels that we want, so that we can then do the second step, and among those, by simulation, find out what's the optimum. It's a bit, it requires a bit of computation, and it's not as easy as if you just used a single model. In particular, if you used the quadratic model, which is linear in the parameters, the optimization there is certainly easier. But going with a single model is exactly not what you want to do if you're not certain what the response function, the real response function, is going to look like. So it's really good to have that flexibility in the approach. Now, moving on to the second part, this is based on another project, and there are 2 papers, but currently it's only 1, but there's 2 others in the pipeline. So Mortesa was formerly with John Deere in Kaiserslautern in Germany, and he works in on-farm experimentation. So the data that he had available and that he worked with come from a farm in southwestern Germany, and that's, you know, farm operations, large fields. The N rates, the farmer determined the N rates using a Yara N sensor. The data were collected in 2020. And the data that he had available were the N amounts applied, spatially explicit, so the positions were referenced, and the yield as well. So we had the yield, we had the amount of N that was actually applied, and then satellite data, multispectral data from which multispectral indices were derived. And at different points before the final N application, these indices were assessed. So this data, and here's a little more information about the data. Yeah, the type of fertilizer applied, the ranges that were applied between 20 and 75 kilograms per hectare in the third dose, different dates at which the spectral data were assessed, and here are the BDCH stages of the crop. And here's the N sensor that was used. So I guess I need to go take a step back and just point out that, well, the farmer wants to determine the optimal N rates, and the Yara sensor is kind of one way of doing it. It's like a black box that tells you what it is. We're going to use a statistical model that uses this data to then derive another model or black box, but it's not going to be a box, it's going to be more transparent because we'll have an explicit model that then can retrospectively say what would have been the optimum here. The key idea is that with this kind of data, although you have this algorithm which tells you how much n to apply in each position, very likely in many cases, the amount of n applied was not optimum. So there's going to be some variation of the actual n applied around the optimum, and that gives us some space to actually fit a curve and then estimate the optimum. So a little more detail about the data, but you guys are more familiar with this than I am. So here we've got the applied n rates, and here we've got the grain mass mapped, and here's the vegetation index, and so all that information needs to be integrated. I mean, it's a complex process, and Morteza worked a lot about developing a pipeline, how to integrate all of these data. And there's a lot of steps before you can even think about the statistical part, which I will be focusing on. You know, you need to align the data that have different, so the actual positions you've got in your data where the n was applied and the positions where the yield was measured or assigned to, they need to be aligned and so forth. So data cleaning is a very important step. These data are very noisy, and you invested a lot of time to try and remove outliers and get data that are really producing robust results. So after these steps, and after the computation of the vegetation indices, we then use variable selection techniques. We use the lasso among others. So there's lots of indices, 21, that's quite a lot of indices. So we could try and integrate all of them, but we actually decided to do a variable selection so that we could focus on a limited number of vegetation indices. So this is just to represent the data cleaning. So here's a response surface. We're going to fit a response surface here. So in a nutshell, this is already showing the type of model that we want to fit. So we've got the applied n rate, and here we've got the vegetation index value on the x and y axis, and then on the z axis, you've got yield. So that's the kind of model that we're fitting. So this is just the before and after the cleaning, just to indicate that that's an important prior step. But here's the model that we used. It's a response surface regression model, second order. It's your quadratic regression as far as n is concerned. It's also a quadratic regression on the spectral index, which I've denoted by x. So you've got the linear and quadratic terms in n, you've got linear and quadratic terms in x, plus you've got the cross product. That's response surface regression. I mean, there's many other models you could use for this, but this one is particularly convenient. It's also particularly convenient because, among other things, because you can easily extend it to incorporate multiple indices. For each of those, you just add linear, quadratic, and the cross product terms. And why do we think this is a useful model? Well, you can then, at each point in the field, you can check, okay, what are the values for my vegetation indices? You plug them into the model, you condition on the values of the vegetation indices that you've observed, and what you get is a simple quadratic model for n, where your coefficients for intercept and the linear term, C0 and C1, are themselves linear functions of the index values, the vegetation index values. And because the coefficients change, I mean, the values of the vegetation index or indices change across the field, and so the values of the coefficients change. In particular, the value of C1 changes across the field, and as a result, the economic optimum rate changes across the field. That's the key aspect there. So this makes this a spatially varying thing, and that's why we think it is useful. So here is just an overview of all the vegetation indices. Again, I'm not going to go into the details, just to, of course, you know, you have to have a lot of subject matter knowledge to know which indices make sense, and I'm not an expert at that at all. But these are the ones that we did include, and we chose specific dates which were prior to the application. Of course, you could also think about other things, but because this is about prediction, you want to measure the indices at relevant stages prior to the point where you want to apply the nitrogen. So here's the model that came out of that selection process for one field. So that looked a bit busy, but it's really just the linear and quadratic term for n, that's in the front here. And then you've got linear and quadratic for vegetation indices. And you also see a couple of cross products between the amount of nitrogen and the vegetation index. So, and when you plug in, as I've said before, when you plug in the observed values of all these vegetation indices, at any given point, you can have a local quadratic model at that point. So this table just illustrates the process. So for each point, so each row in this table is one point in the field. Here are the vegetation indices and their values. And then you plug them into the equation, and you get these values in this first point here for C0 and C1. C2 is always the same because that's just the coefficient for the quadratic term. The quadratic is just always there in isolation. It's never crossed with anything. You could do that. That makes the model more complicated. But C2 doesn't change, but C0 and C1 do change across the field. So you go down, you see C0 changes and the C1 changes, and the economic optimum rate that comes out, that to the side here. So you've got varying optimum rates that come out of this. And here's just an illustration of two instances, 2 points in the field where both you have a quadratic model, but the optimum changes. And another illustration, 5 points, so a bunch of lines. So then you can map the economic optimum rate. This is a map showing the values and a histogram showing the range of values. So the range is between 45 and 75-ish. So that's nice. I mean, this is kind of based on a given trial. So it's kind of, what's the use of a farm of this kind of exercise at this point? You can use it to check retrospectively, what did I apply and what would have been the optimum. So that's probably useful information. But of course, the next step is try and use that model and apply it for the same field next year. But how transferable is that? That's the critical. And we've explored it to some extent, but that's something that certainly needs further research. But so the main message here is the type of modeling that we hope is useful. We've done some cross-validation. So he had 5 fields. He had a couple of more, but he picked 5 that really gave nice results and were from the same farm. Here also we used the model averaging idea. So we fitted this kind of model for each of the fields, and then we averaged. But this time we're not modeling different types of model, but we're modeling the same type of model, but with different estimates of the parameters, each field specific. And here's just some summary results. So our root mean squared error, based on this approach, using a leave one field out cross-validation approach, was 11 kilograms of nitrogen. That was the root mean squared error. An alternative that we tried was a pooled model. The pooled model being obtained by just pooling all the data from the fields used for estimating the model, lumping them together, and fitting just one response surface rather than fitting one for each field and then averaging across the fields. That didn't work so well. The root mean squared error was about twice as large. And so we think that model averaging here in this slightly different sense is also a useful thing. Okay. Yeah, that's about it. this is just an outlook. So I'm collaborating with Gia Liu at CSIRO in Canberra on, again, a design question. So what's the optimal design for this? And I mean, this is just a routine field operation. So there's no design other than that you've got the Yara sensor telling you how much N to apply. You could say that's a design. Well, it does work in the sense that, yes, I can estimate the model, but can I get a more accurate estimate of the model? And if I'm a farmer, can I do my own experiment? So can I use my field and then say, okay, how do I choose the N levels in my field so that I can get an accurate estimate of that response surface model? So the idea that we're pursuing is that based on the current year's data, the current fit, what is the economic optimum rate, or based on a model that you fitted using past data, estimate for each point in the field, what is the economic optimum rate? And then, or before doing that, ask the farmer, how much deviation from the optimum are you willing to tolerate? I mean, of course, normally I would want to apply the optimum rate. That's why I determined it. If you want to estimate the model, you need to deviate from the optimum below and above a little bit. So you have some variation, so you can fit that curve, basically. So the idea is, ask the farmer, how much minus or plus away from the optimum are you willing to tolerate? Are you willing to tolerate plus or minus 10 kilograms of N? Then within that range, the design problem becomes, okay, within that range, where do we place the N level for this particular point in the field and for any point in the field? That's the kind of design problem we want to tackle using a Bayesian framework. But that's work that is still, it's only just starting. Right, and with that, I think I'm at the end of my talk. Here's the references, and I'm happy to take questions. Yes.
Wonderful presentation. Obviously, a lot of learning from you. So I have used EONRs, and my only concern is that when the prices are not stable, because N prices, if your bushel price is higher for corn, it basically encourages farmers to apply more nitrogen, because your bushel price are higher, and every bushel goes up, the applied nitrogen, you have more profit margin. So where to stop?
Where to stop in terms of the amount of nitrogen to put on?
Yes.
Well, I guess from an environmental perspective, stop right where economic optimum rate is. But then economic optimum rate is a moving target as well. Yeah. So I think that's an ideal task for a Bayesian framework where you can build in the uncertainty about prices as well. I've treated them as fixed quantities here, but it's probably much better to use historical data or use price projections and build that into the Bayesian framework. That would be an ideal thing to do in a very nice extension.
So the other question that technically UNR is, you average the models, and each model has its error that attached to it. So when you're adding that, isn't it you adding the error as well down the line?
I'm adding, but actually I'm averaging.
Yes.
And averaging is better than adding in a way. I'm really averaging. That's why, and that's why it's actually getting better, because it's allowing that flexibility. I mean, if I have a single model and the model is wrong, then I have bias.
So for example, if you have an X model which performed the best, we see A1C value as well as R square value, right?
Yes.
So you found that this is an X model that is performing very well. And now you have weak models that you are also averaging with them.
Yes.
So you're adding the weak model to it. You understand the question?
I understand the question. I think you're kind of working from the premise that the model you've identified by AIC is truly the best model. And it is truly the best in terms of, yes, it's optimizing AIC. But there's also an uncertainty in the AIC itself. AIC is also an estimate of the Kullback-Leibler discrepancy between the true underlying model, which we never know, and your candidate. But it's based on the data, it's based on the likelihood. So it's just an estimate of that discrepancy. So there's that uncertainty as well. That's the whole point. We are making a model selection and then we pretend that this is the true model, or this is truly best model. But we can't be sure that that's actually the case. It may well be the case that actually one of the other models gives a better fit. I mean, we need to make that distinction between I'm fitting a model. Just take a simple case, straight line regression. You have a scatter of points and you're fitting a straight line. You're doing method of least squares, so that's like the best fit. What we're doing is we're trying to bring the fitted model close to the observed data. The fitted model is, but we need to keep in mind that the fitted model is just an estimate of an underlying true model. So that uncertainty also needs to be built in. It may actually be the wrong candidate. That's the other thing. So, yeah, how do I wrap this up? I mean, the point is there is the model uncertainty. There is the model uncertainty that we need to factor in, and that's what the model averaging does. And that's why it's usually performing better. And I mean, it has many areas of application where really you have very complex models, and very often you are actually better off by averaging a bunch of models rather than settling for one. Even though standard metrics will tell you this is the best model, but that's just estimates. So there's always the uncertainty that remains.
May I ask a follow-up question, and it's actually regarding the model averaging. So first, maybe a little comment. So this doesn't contradict your point, because if there is a truly best dominating model, then it's going to get weight close to 1 or 1, and everything else gets weight 0. So you are not losing, at least conceptually. So this is more flexible. But my question is the following. So the way you expressed it, it looked like you have the nonlinear regression, where the regression function is a mixture of your specific regression functions.
Mm-hmm.
And then you place a Dirichlet prior on the weights. Yeah. But in Bayesian model averaging, there is often a different approach that's used.
Mm-hmm.
So that is, we have, say, 5 nonlinear regression models, M1 through M5. So given the model, we have a specific regression function.
Mm-hmm.
And then there are no doubles. Basically, the averaging happens automatically through Bayesian machinery, and the weights are
Mm-hmm.
the model posterior probabilities where we have marginalized over all the parameters. So, but are you doing something different from what I described? Because you have this Dirichlet layer. And if so, what are the advantages of what you're doing?
Yeah, that's a good point. You could do it differently. And so we really build in the W's there as parameters of a model. So it's really a combined model, which is slightly different from what you explained, which is another alternative. We haven't systematically compared the two, but that would be actually an interesting comparison. Which of the two is the more powerful approach?
I'm not saying one is better than the other. It's that what I described is how it's typically done.
Yes.
In the case of any models, like even
Yes.
multiple linear regression
Yes.
models, where the model is a subset of covariates.
Yeah.
And so, if I may continue, also,
yeah, but maybe just to add, so this was actually particularly convenient for the design optimization. That's why we chose that framework primarily, not because we thought it was the better option necessarily. So that could be an interesting comparison. But one would have to think carefully how to really use that in the design optimization.
Mm-hmm. And also related to this mixture of the models. So I'm, having some experience with Bayesian statistics, I'm assuming that it's not an off-the-shelf approach, it's more of a direction through which it will be followed. Specifically that you wouldn't pick like any random models. There is some homework that needs to be done. So first, one probably needs to check whether a given model like a quadratic or a linear Plateau model is adequate for the data.
Mm-hmm.
Yeah, because what we and I'm sure for nitrogen it is, but it's that I'm working with a different fertilizer, phosphorus, and for some sites, this plateau model just doesn't work.
Mhm, mhm.
And the question is, how would one diagnose the departures? Because is it a pre-processing step that needs to be done before we proceed with this selection of the nonlinear regression functions of particular shape? Or maybe there is some step, diagnostic step in the procedure that you presented that would allow to capture this inadequacies.
Mhm. We didn't use a specific procedure to come up with this set of models. I think this is mostly based on just experience that these are the types of models that typically are used in and fertilizer studies, and they typically give a good fit. So I guess something along those lines needs to be done for if you've got another nutrient then and the linear plateau doesn't fit, you probably wouldn't include that in the model averaging here. It's probably good to have that preliminary step and say, okay, we're not going to use each and every model, a lot of which may just be nonsense to even try and fit, but only fit the ones that are really promising, I guess, is the idea. But I mean, that's more or less stating obvious. But you know, other than that, we didn't use any specific procedure, and I don't have a specific procedure to propose at this point of how to proceed there.
Oh, you mentioned the lack of fit diagnostic, which is essentially comparing how each model would fit versus the.
Yeah, I mean, empirically, you could, of course, you probably will try different models and have some sense, but that's rather subjective, I guess, in a way, of what fits well, and also in terms of the subject matter, what makes sense. Like if in phosphorus, you have that increase keeps going, then the linear plateau doesn't make sense, and you have a lot of empirical evidence from past trials, then you're not going to include that as a candidate. That's so. But it's probably good to not throw in too many models. Really be selective and really pick the ones that you think are promising. But a formalized procedure, I don't know how to do that. One could probably think of many different ways of doing it. I think common sense and really looking at the empirical evidence is case by case. That's what most people would do.
Thank you. I have also questions, but I don't want to hijack that discussion. Thank you very much for the wonderful presentation.
In the chat. So
if you can read them all.
Yeah, so I just put in the chat and ask everyone online to put in questions in the Q&A, but I do not see any at this time.
okay.
The Q&A.
Oh, good.
Ah,
I do
okay.
not have access.
The zero. Okay.
Okay, repeat it.
So in a previous talk, we heard about the importance of including a zero or no fertilizer treatment. However, my table doesn't have a zero treatment. So my design optimization just left that completely open. It just said anywhere between 0 and the maximum that we specified. So there's a lot of good reason to have that control in there. So you can put that as a constraint and say, we want 0. That's going to be one of the levels. So where do we put the other levels? That you could do that, of course. But the optimization says, in terms of estimating the economic optimum rate, it's not a good idea to put the 0 level, if that's your sole purpose. But like I said, there's other reasons to wanting to have that control in there. You plug it in, you pay a price, a little loss of inefficiency. Okay, conditioning on that, what's the optimum placement of the other rates? Yeah, can be done.
In your design component, this is basically a single factor experiment.
Yes.
Can you expand this to factorials? So if you have 2 or 3 varieties where you want to calculate this, let's say for an early, medium, or late maturing cultivar, or I don't know, water management or something like that.
So cultivar is probably easy. You could just say, I'm going to look at one cultivar at a time. I mean, if you do multiple cultivars, you want to have the optimal, you want to fit the curve for each cultivar. And you may do one cultivar at a time. Your priors may be different for the different cultivars, so that would be reflected in your prior specification. And then you might have different placements of the rates for the different cultivars. So that should be relatively easy. The more tricky extension is when you have another fertilizer input, say P. So you want to then optimize across P and N levels. And then how do you extend these nonlinear models to accommodate two inputs? That's more tricky. Unless you stick with linear and quadratic, they're relatively easy to do. So I guess it's a matter of, can you come up with the component nonlinear models that allow you to extend that, and that can be done. And then use those and plug them in principle. It's possible, straightforward.
In the early tables, you showed the more levels you have, the fewer replicates you need, or because you have that constraint in there, right?
Yes.
But
yeah, that was just a result of the constraint, because as I said, we have this capacity of 120. If you then took the next step and ask, okay, to get a specific precision, such as I want to have my standard error of my estimated economic optimum rate to be no larger than this value. So how many replicates do I need? That would be an extra step. And then what would probably happen is that if you choose the optimum number of rates, your number of reps per level would be lower than if you increase beyond what's actually necessary. In terms of total number of plots, you would need more plots to get the same precision. Yeah, so those numbers were not the optimal ones in terms of overall precision. It's really like conditional. This is the capacity. What's the best use of that capacity?
But just to clarify about the design search. So basically, we have a fixed budget, like 120 that we have, and that is the product of the number of rates and number of reps, if I assume. And then the goal is to determine what's the number of rates, the number of reps, and also the placement of the rates.
Yes.
Because those are not assumed to be uniformly.
Yes.
Right.
Yes.
It's a hard problem.
Yeah. And if you look at this for individual models, nonlinear models, relatively simple, just some exponential, a model that approaches an asymptote. You get placements of the rates. If you say I want the optimal design for 3 levels, they can be very unevenly placed. And where they are placed does depend on, that's the tricky bit. The placement depends on the values of the parameters as well. And that's where the Bayesian framework is very useful, because you can then allow for some flexibility there and or prior information if you have strong prior information.
Yeah, I think one needs to spend most of the budget to detect that this region where the function changes, because when it's flat, you do not need many rates there.
Yes.
If it's indeed.
Yes. And that's what this approach should actually achieve.
I have a question about your own farm trial. When you said that you selected a good responsive sites, what was the percentage of the sites that you selected that yielded the functional model versus what was available? Was it roughly 50%, 40%?
I think we had 7 fields or 8, and we selected 5.
And here is where I'm going with this. So I would assume that if the fields were on the same farm, the conditions were very similar in terms of weather, soil.
Yes.
How robust do you think the model would be if you would want to stretch it in terms of, for example, soil conditions? If you would have something very sandy transitioning into maybe that's something loamy versus even heavier soil, do you think that it would be robust enough to handle this big of a change, or?
That's a very good question, and I don't have an answer to that. I can't really have an answer for that based on what we've done. It's very limited, really. But maybe soil properties are worth also putting into the model, if you want, and you can do that. I mean, this response surface regression approach, the nicety is really you can just add on further useful explanatory parameters if you can assess soil quality.
We did that. I can answer that. We did that. It's a beautiful example in Oxford State, and they have divided the recommendation depending on the soil texture. So there's the heavy heavier soils, clay percentage around 80%. And then there's a medium texture, which is around 30%. And there is a little bit more loamy side that is like a 15% clay. But
Yes.
those are individual models, right? The model actually
That's
gives
right.
them the, yes, individual model.
Actually, this trial that we used actually had two sections that also differed in the amount of loam. And they did the same thing, and they also found the economic optimum to differ slightly between the two. It wasn't significantly different, but anyway, numerically it made sense. But yeah, like I said, it's a good point. It's like two separate models.
Yeah.
And trying to have a single model where the amount of loam, the percentage, is an extra predictor. That I think is a promising way forward if this were to be extended to other sites that are really different in soil type and maybe other environmental conditions, rainfall and things like that could also be incorporated into that framework.
Now incorporate resource limitation in your planning. How would you do that?
Limitation of which
we have limited resources in terms of field space, labor, and so on. And that's often a very critical component in the planning at a fertilizer rate study. I mean, your scenario was 120 plots.
Mhm.
That's a large number of plots.
That's
So,
right.
the point is, so if our resources are limited, what do we do?
Good question. Well, if you're limited on resources, and that might mean you're just limited on the number of plots that you can use. Work with that number and maybe much lower than 120, and then find the optimum and having optimum design. And given the optimum design, try and estimate what the precision of your estimate is going to be. And then sit down and think twice. Is this accurate enough, or is this so wild that I better not waste the resources at all? That's the usual thing that's to be considered when you design a study and the sample size isn't large enough to give you the precision that you would need. Don't do the study, I guess, would be one answer. But yeah, I don't know. How would you see that?
Don't ask a question, what's the question of? No, I mean, that's a point that we face, that's a fact we face in practice.
Mhm.
And yes, but then the question is, okay, we come up with this optimum and we find the optimum response, and that confidence interval is yay big. And so throw up your hands, so we don't do anything. We don't do the trial, because that would be the conclusion, because we would be wasting money. So the only way is really to acquire more resources. Yeah, and in particular, I guess I just looking at you there, it's a trial, your field space is limited there.
Yes,
We've done trials where we have to well, squeeze them in.
adding one treatment to their lot many dollars to the total budget.
Yeah.
So just between 5 and 6 treatment is a huge difference in the total cost.
But if it's this on-farm trial setting in my second example, maybe the cost, because this is a routine operation anyway, you're going to monitor the amount of nitrogen applied anyway, you're going to monitor the yield anyway. There's a lot of data. Maybe that's much cheaper.
Yeah, we have some on-farm trials that didn't go the way we were kind of anticipating. So those are some kind of.
Yeah.
Skeptical.
Yeah.
About the success of those, and when you're not tenured, things are a little more.
Any other questions for the room? I don't see any other questions online. So thank you very, very much.
Anyone who wants to continue the discussion, we're going to meet at the first magnitude around 5. So.